So let me just start the class then, since there is okay. Yeah. Uh, so basically the plan is to finish one question from the, I think, last assignment. One derivation was left because of the shortage of time. The derivation was quite uh, a long derivation. Um, so I'll finish that part, and afterwards I'll just solve this last week's assignment to you. And then if there is time and if you need, then I can discuss some of the hints to solve how to solve the next week's assignment, and we'll fully solve that in the next class as we follow in the general tutorials. Okay, so just let me take a look at the question that I am going to derive now. So this is question number 5. As I did not get the chance to derive it in the last class, and hence I'll first start deriving this in the current class, and then I'll start the this week's thing. Okay, so let me just take a screenshot of that so that yeah. Um, then let us begin. Fine. So hopefully I am properly audible and the screen is visible to you. And if at any point, if as you know that if you have any doubt or any problem, you can just unmute yourself and let me know. Otherwise I'll just continue deriving it on my own. Okay, so now this particular derivation is a bit like lengthy derivation, but if we follow step by step, then there will be a less chance to do a mistake. Okay, so let me start. First of all, this is from last week's assignments. Okay, question number 5. So now let us read the question first. It is saying that for a gas of non-relativistic fermions in 3 dimensions, a leading contribution to entropy at high temperatures may be written as some expression. That expression we need to derive. And so let us first look at the clues that are given. What are the clues that are given about the system? First of all, it is a fermions. That means it is a Fermi gas. That means the gas molecules actually follows the Fermi Dirac statistics. Okay, first of all that, and then it is also mentioned that it is in the non-relativistic limit. Okay, this is very important, that which limit is being used. Depending on that, the type of derivation will change. So non-relativistic limit means the velocity of the system, or the, let's say in this case the gas molecules, is actually much smaller than the speed of light. That means if you can say that this can be written as h cut sum k is much smaller than mc. This is I am writing in the momentum terms. Momentum is basically can be written as h cut times k. You know, k is a wave vector, and m times c, that means the momentum that is equivalent to the speed of light c. So when we are in the non-relativistic limit, we assume that the system that we are dealing with has a velocity that is much smaller than the velocity of light. That is why it is a non-relativistic limit. And also it is mentioned in the question that we have to deal this problem in 3 dimension or 3D. Now there is one last thing that actually is crucial, is that it is asked to get the derivation for high temperature. Okay, entropy, you have to derive the entropy expression at high temperature and only up to the leading contribution in temperature. That means let's say you, if you derive your entropy, which is some S will be a function of all the other macroscopic properties of the system, like volume, it can be number of particles, or these things. Okay, it can also be a function of the internal energy U. So this is the entropy of the system of gas molecules in this case, and you have to derive its expression um, up to leading order in temperature at the high temperature limit. At high temperature limit. That means you can assume that your temperature T may be tending to infinity. Or in other words, you can say it like that the beta, which is basically inverse of temperature, will actually go to 0 when the temperature is very high. So if T tending to infinity or beta tending to 0, so basically this limit you have to consider or keep in mind whenever you are starting to solve the derivation for entropy. Okay, now so this part is fine. So basically we'll now start with the general formula that is already there in the lecture. So we'll directly use that so that some part of the derivation is actually becomes less complicated, because anyway those derivations are done in the lecture itself. Okay, so let us start with the energy density first, which is this U subscript of V. This is the energy, internal energy divided by the volume, energy density. And in your lecture you can find that this is expressed in a general expression of d cube r divided by c naught beta, then multiplied by r squared by e to the power of r squared into e to the power of minus beta mu. Mu is the chemical potential, you know, plus q. Now here you know that this is a general expression where q value can have values of either +1, -1 or 0. So when we are dealing with Fermi gas or fermions, then q will be +1 because this is fermions. If the question was given for bosons, then we have to take q equal to -1. So it is equal to -1 for bosons and +1 for fermions, and when we are dealing with not quantum but classical particles, then q value will be 0. Unlike these boson and fermions, which are quantum particles, where q can have a non-zero value of either +1 and -1, but when the problem is with classical particles, then the q value should be taken as 0. So this is the general rule, and this is the thing that is already given in your lecture. This is the general expression. Now you can see here there is dq bar. This is because the integral is done in 3D, because we are asked to deal the problem in 3 dimension. As so yes, all basically we are following the instruction that is given to us. And C0 you already know from the last class also. I derived a similar kind of a problem, but in that problem I think the question was given to take the low temperature limit for fermions, but nevertheless the constants become the same. So C0 is nothing but your thermal de Broglie wavelength. Okay, so you know the expression of it. This is that C0, right? So that is there. And so C0 value, let me check what was the value of C0. Let me write it down. So C0 value was basically I think 2 beta pi square h cut square divided by m to the power of half. So this was your value of C0, and this thing we will continue in the derivation in some parts. So let us then start the rest part of the derivation. So here for simplicity we'll define another function in this case, which is this function. Let's say g, and you have q in the superscript and n as a subscript. So q is any general function that is defined as this r to the power of 2n divided by e to the power of r squared, and then z to the power of -1 plus q, then d cube r. So this is a general expression of the function gqn that is defined here. And here z is, you know, that is this is the e to the power of beta mu. Mu is the chemical potential, and z is here like notified mentioned as fugality. This is also known from the lecture. So this is the idea of z, that z is equal to e to the power of beta mu, right? And so here in the formula of Gn, this is the general expression. Also for fermions you have to directly put q equal to +1, right, in this expression. But then the n value can also take different values, right? Like n value can be n from 0, n equal to 1. These different index values can be taken, and based on that the expression of the function will change. So basically because I said that for fermions q equal to 1, so let us put q1 in the superscript. Instead of q we put 1, and then let us identify different values for different n values, right? For like say n equal to 0, then you have this as r to the power 0, that means you basically have nothing but 1, and then here you have the power r square z inverse, because q equal to 1, so this is plus 1, and then dq bar. So basically, because r to the power 0 is 1, you are just left with this expression where there is 1 by this thing, okay. And similarly, you can also take out what is the value for n equal to 1, then just put n equal to 1 in the expression. So this is basically r to the power 2 into 1, that means r squared, and the denominator is the same, that is to the power r squared z inverse plus 1 for q equal to plus 1 dq bar. And like that, you can, from the general expression of the function gqn, you can put different values for n, and your q value has to be fixed at 1 because you are given the problem with fermions, and thus this function can be taken with different values. And now once you have obtained this, let us now try to remember what was our idea of uv, that is energy density. Let us go back. So this was our uv, right? So you can get here that here you can see that, once again you can see that in the uv, here is a r square in the numerator, and denominator you have this e to the power r square e to the power minus beta mu plus q. So just look at this expression and you can exactly find out that this total expression is nothing but the general expression of the function, this g11, right? When you put n equal to 1, you get a similar r square in the numerator. So basically you can replace this functional form of g11 in the functional expression of uv, so that you can get the entire expression in terms of the general function of g and then some constant. So how do you write that? You basically, you take out the constant part outside, that is 1 by c naught cube beta. This is independent of the integral, so it comes outside, and then inside the integral, when you replace the function, this is basically g11. So this is basically your entire expression of energy density or uv, right? Yeah, this is basically your total energy by total volume. Now similar by similar means you can also work out the other things that is necessary for this derivation, which is like this particle density, which is rho. Rho is equal to basically total number of particles by total volume. This also has a similar general expression for 3 dimension, and that can be found in the lecture video. So this is basically the expression that I am writing down, that integral dq bar by c naught cube into 1 by e to the power of r squared e to the power of minus beta mu plus q. Okay, so here also again it is the general expression, so we have to put q equal to plus 1 for fermions, and then if you look at the expression, so let us just replace plus 1 directly from here itself, because anyway the problem is given for fermions. So basically this is equal to plus 1. This will be the functional form. And once again, if you look at this function in the integral, you can find a similarity with the expression of g10 that we had seen earlier. So that is the reason we are expressing this general function of g, some value of n and some value of q, because we want to replace that in our main identities. Okay, so similarly you can find out that this expression of g10 we can be replaced in this integral format. So after that, the rho value will be just 1 by c naught cube, and then g, your q value is 1, so it is 1, and n value is 0. So this is again your expression of the particle density n by v or rho for fermions in 3D and in non-relativistic limit. Remember, all of this are only in non-relativistic limit. Non-relativistic in short is NR. Okay. Now, so this is also done. So now here comes the form. We want to deal with actually the functional form of GQN, because ultimately to solve your these different identities of rho and UV, you need to solve the general expression of the function GQN, because in every other integral the GQN has some involvement, right? Because you have expressed GQ with different values of n in the main identities of rho and UV. So to solve for UV and rho, you have to actually get the value of G for different values of n. So keeping that in mind, let us try to solve this integral expression of GQN, which is like this thing r to the power of 2n. I am again writing down the expression of gqn, the general expression. So it is e to the power r squared, then z inverse plus q, right? And there is an integral of d cube r. So now let us try to simplify this thing a bit so that we can actually solve for the integration. So how can we do that? First of all, let us take some part common as outside. Like in the denominator, what we do is that we take e to the power r squared and z inverse as a common to the outside, and so it becomes inside the bracket it is just 1 plus then q, because we have taken this part outside, so we have to adjust it as e to the power minus r squared into z in the second term. So this is the thing that we have taken out, and basically we have adjusted the forms like that, and pretty soon it will be clear why we have adjusted terms like that. It is basically because we want to solve the integral in a doable form. So after the simplification, let us take this z inverse as z on the top. So it is z e to the power of, again e to the power of r square also it comes up as e to the power of minus r square, and this is just r to the power 2n as it was from before, and this is just 1 plus q e to the power of minus r squared into z in the denominator. So this is the form that we obtain. Now this dq bar, because it is in 3D, so you can just replace the dq bar as 4 pi r square dr. So you know this r are just the positional coordinates, just we are familiar with in most of the cases. This is the integrand also. So you can write this volume element of dq r as 4 pi r square dr. This is familiar to you, I hope. So this is r to the power of 2n, and then dq bar is just 4 pi r squared dr, right? And then divided by, it is just 1 plus q e to the power of minus r squared into z, right? Okay, fine. Then this g qn, this function, what it becomes is that you just take the constant 4 pi outside, and this is just dr. Now let us compile terms that are similar to one side, like r to the power 2n and r square, we combine them together. So this is basically r to the power of 2n plus 1. We just have multiplied them together, and then we are left with just z and e to the power of minus r squared, and this denominator we take it up as e to the power of minus r square q into z, and this whole thing inverse. Okay, now here comes the time when we have to utilize our condition that we have to deal with high temperature limit. Okay, so here is a point has come where we have to actually apply the limit to the problem so that we can solve the integration further. So if temperature is very large or high temperature, then your beta is definitely very small, because beta is equal to just 1 by t, beta equal to 1 by t, right? So if beta is very small, then e to the power of beta mu is also very small, because ultimately it is just a small term in the exponential, so it makes the whole thing very small. So do not forget that this e to the power beta mu is actually defined as our fugality or z. So that means your high temperature limit actually gives you the condition that your z value is very, very small. Okay, so this is the same limiting condition, only that you have rephrased the whole thing so that you are not defining in terms of temperature but related to temperature. You have found out that because high temperature ultimately leads you to a small beta value, so it is ultimately leading you to the z value to be very small, because z equal to e to the power of beta mu. So once that condition is clear, then you can actually understand why I have used this condition, why I am to use this condition here. So basically here you can see, this is, you can think of it like 1 plus some x to the power of minus 1. So if you know that binomial expansion can be done, or binomial simplification can be done, if x is much smaller than 1, then you can just very simply approximate this term as 1 minus x, and then all the higher order terms like x squared by 2 factorial, all these, they are cancelled out because they are higher order terms and x is very small, so they cancel out to be 0, and you can simply approximate this thing by binomial approximation as 1 minus x. So similar thing can be done with this 1 plus q e to the power minus r squared into z inverse. Because z is very small, so this whole term is actually much smaller than 1. You can assume that, right? It's a small term than 1, so you can approximate it in a binomial fashion. So this is just 1 minus q e to the power of minus r squared into z. So this is your approximation that you have to use under this condition of T very large or high temperature. So after that, again write down the expression of GQN. So your GQN becomes 4 pi and then dr r to the power of 2 in plus 1, then z e to the power of minus r squared, and then this binomial approximation you can convert it like 1 minus e to the power of minus r squared into q into z. So you have just replaced this minus 1 by this binomial approximated terms, and this comes out like this. So again you can like separate out the two terms in this minus subtraction, so that you can have two different terms, first term and second term, in the integral limit. So this 4 pi, keep it as it is in the outside or in with every term, or also take out this term z also, because that is also independent from the integral of dr. So take out this 4 pi z outside, and you are left with the first term is r to the power of 2 in plus 1, then e to the power of minus r squared into dr. So this is your first term because it is multiplied with plus 1, right? So this is your first term, and then for the second term you have to multiply the whole thing by the second term, which has a minus sign to the front of it. So you just multiply it like minus of, it is just r to the power of 2 in plus 1, then multiplied by z because there is a z in this second term, and not just is it z? Yeah, it is just z because we have taken out this z outside as a common factor. Remember, do not confuse that with this. So this is a common z that is outside, and the second z that I am writing in the second term is actually from this term over here. So this is r to the power of 2n plus 1, and then z, and then e to the power of minus r squared into, what I am missing out is basically, oh, so there is another minus r square, so they will be multiplied and become e to the power minus 2r squared, and then it is also there is a q term, and then as simple the integrand is dr. So this is your first and second term of the integral. So now we'll try to solve the two term of integration one by one, so that ultimately we can write down the final integration result. Okay, so let us try that. So the first term is this term. So how can we solve that? So let us take only the integration part of the first part. So this is, remember this r was from 0 to infinity, we know the integral limit. So, and inside it is just 2 into n plus 1 to the power of minus r squared and dr. So now let us make some substitution of terms, like let's say redefine r squared by some another variable of t. Okay, this is just for simplicity of the calculation of integration. So let us redefine r square as t, so that your 2r dr becomes dt. And so if r is going from 0 to infinity, t will also go from 0 to infinity, that we can know from the relation. And now replace everything in the integral from r to in terms of t. How to do that? It is just, again, that limit is same, 0 to infinity. R to the power 2 into n plus 1, that means you have basically, if r square is t, then r is equal to root over of t. So it is basically root over of t to the power of 2 in plus 1, and e to the power minus r square is e to the power of minus t. Then dr is basically your dt divided by 2r, right? So dr equal to dt by 2r, but then you want everything in terms of t, so you again replace this r by t itself, so it is dt by 2 root over of t. So now your integral has been changed its form from the variable r to variable t, and so simplify it, just simplify it step by step. So this is 0 to infinity, and e to the power of minus t comes to the front, and this is just divided by 2, and this was root over t to the power 2n plus 2 here, and there is a denominator, it had another root over t. That means if you simplify, you will just get root over t to the power of 2n plus 2, and this minus 1 because of this term, and dt. So this is basically 2n plus 1 in the root over t limit. So how we can write that? This is just 0 to infinity to the power of minus t divided by 2, then t to the power of, so 2n plus 1, and then there was t to the power half. So if you adjust both of them, it will become n plus half. Okay, n plus half, and then it is dt. Now if you look at it very carefully, you will see that it is in a known form of the function. This is basically the definition of gamma function you can use. So this is your gamma function definition you can use here. So basically your gamma function used to be defined like gamma of n plus 1 equal to 0 to infinity e to the power of minus x, let's say x is the variable, then x to the power of n dx. So here if you try to find a similarity with the gamma function, you will see that here your x is basically t here. So 0 to infinity, then half comes outside, e to the power of minus t, and then your x to the power n is here, t to the power of n plus 2. That means here here your n is basically replaced by n plus not 2, n plus half. So n plus half dt. So what is your gamma function value then? So it is basically was n gamma n plus 1, but in this case your n is n plus half, so you get gamma n plus half plus 1. Alright, so this is a known form, you know that it is just half simplified like gamma n plus 3 by 2. This is your value of the first term of the integral, very easily solvable because we knew that it was coming in the form of a known gamma function. So now this is the turn of the second term, that is r to the power 2 n plus 1 z e to the power minus r square q dr. Okay, so let us only take the integral from the second term also. Second term's integral part is just 0 to infinity z e to the power of minus 2r squared q r to the power of 2 n plus 1 into dr. So let us look at whether we have written it right or not. So this was z, we have written it r to the power 2 n plus 1 e to the power minus 2r square into q. So all the terms are taken. Now again we have to make some redefinition of the term so that we can easily solve the integration like in the first term we also did, but in this case instead of r square we take the new variable t, define it as 2r squared, because this is your exponential has 2r squared now. So to simplify, you take t equal to 2r squared, and basically it makes your dt equal to 2 into 2r times dr, so that is 4r dr. So your dr basically becomes dt by 4r, okay, which is and also here from here you know that your r is just root over of t by 2, okay. And so similar way you have to replace all the terms here so that you can express the in terms of, instead of in terms of r, you have to now express in terms of the new variable t. So the limit will be same, 0 to infinity. Now z is z fugality e to the power beta mu, that remains the same because that has nothing to do with the integral of r. Now only e to the power minus 2r square becomes e to the power minus t. Then q remains as it is because q is just a constant value that is again there, and r to the power 2n plus 1 becomes your t by 2 to the power of 2 n plus 1 divided by 2, because there is a square root. So we take this half and adjust it with the main power. This is just t by 2 to the power n plus 1, and dr is just your dt divided by 4r, where r is root over of t by 2. So I can try to readjust the terms. So take out this z and q because they are outside the integral, no dependence on the integral, and this is just Okay, there was this 1 by 4, 2 into 4, that means here this is 8. Okay, 8. And this root over 2, if it comes in the numerator, it becomes 1 by root over 2, so it becomes root over 2 on the top numerator, and rest of the terms are e to the power of minus t, then t to the power of, sorry, I made a mistake over here, this was just 2 to the power n plus 1, not just 2, so I cannot write it like 8, because this is just 2 to the power n plus 1 I have to take. So what will be the terms then? It is 2 to the power of n plus 1 from this term, and there was another 4 from here, so this is just 4 into 2 to the power of n plus 1, and this is just e to the power minus t, t to the power of n plus 1, then root over t, because there is this root over t, so you can adjust it with this, so this is n plus 1 minus half, then dt. So I have not missed any term, so let us do it very carefully. This is just z cube, then divided by 4 into 2 to the power of, so this n plus 1 and then half adjusted with this, it makes it n plus 1 minus half, so this is basically n plus half, 2 to the power of n plus half. Then this is so after that you get 0 to infinity e to the power of minus t, t to the power of n plus half again, and dt. So again you see the familiar form of the known gamma function, and so you express it like 4 into t to the power of n plus half, and this gamma function tells you that this is just gamma, again n plus half plus 1, or gamma 3 by 2. So your final form is again z cube by 4 into 2 to the power of n plus half into gamma n plus 3 by 2. So this is also derived. Then you just have to replace these two values of integration in the two terms above, so that you can get the entire expression of GQN. So what was GQN? GQN was just your 4 pi z multiplied by the first term minus the second term. So the first part was half gamma n plus 3 by 2, and this is the second part. So your general GQN value is just 4 pi z to half gamma n plus 3 by 2 minus z cube by 4 to the power of n plus half gamma n plus 3 by 2. So if you adjust the terms a little bit, you get this 2 pi z. So we basically take out the first term as common, that means half gamma n plus 3 by 2 take out as common, so it cancels out with 4, so it is 2 pi z. And then if you take common of gamma n plus 3 by 2, so the first term just becomes 1, and the second term, how can we adjust that? So this is we have taken out half, right? So 1, 2 will be less from this part, so this is just 2 from the 4, this is just 2 left. So if 2 is left and there was already 2 to the power n plus half and another 2, that means it is 2 to the power n plus half plus 1, so it is 2 to the power of n plus 3 by 2. And again because you have taken out gamma n plus 3 by 2 already, so this there is no other part that is left. Okay, now just simplify. So this is just your so I think I have already simplified. This is just 2 pi z gamma function of n plus 3 by 2, then in the bracket 1 minus z cube divided by 2 to the power of n plus 3 by 2. So if that is done, now you can just go ahead, because you have already obtained your functional value of the GQN. So you can now put any value of n or q and you can get the value of the function. So in the UV, you can remember that your UV was redefined in terms of this GQ as GQ equal to 1, because you have to put q equal to 1 for Fermions, and n equal to 1, divided by if you remember the earlier expression, it was C naught cube beta. Okay, it was C naught cube beta. So now this is 1 by C naught cube beta, and then this GQ1 you have to replace the value of this So you write 2 pi z, then gamma, because n equal to 1, so you get 1 plus 3 by 2. What is that? 1 plus 3 by 2 is 5 by 2, gamma 5 by 2. And then in the bracket 1 minus zq divided by 2 to the power of 1 plus 3 by 2 is again 2 to the power of 5 by 2. So you have just replaced the value of this function with putting or plugging in the value n equal to 1. Okay. And ultimately we have to take q equal to 1. So also there is this no q in this case. This is just z times 1. So we have plugged in n equal to 1 and q equal to 1. So what is your final expression of energy density UV? UV is just 2 pi z divided by C naught cube beta into 1 minus z to the power of 2 to the power 5 by 2, then gamma of 5 by 2. So this is one expression already done. Okay. And similar pattern we can also solve for rho, that was your n by v, and this was also expressed in terms of g by g q equal to 1 and n equal to 0 divided by just c naught q. So now you just have to plug in the value of q equal to 1 and n equal to 0 in the common formula of g function, this case. So you put n equal to 0, that means you are only gamma 3 by 2. So let us write it how this turns out. It is just 1 by c naught cube into 2 pi z into 1 minus z to the power, because now n equal to 0, so it is just z to the power 3 by 2 instead of 5 by 2. And also for the gamma function, it is again n equal to 0, so it is just 3 by 2. Okay, so this is your value of rho. Okay. So once you are done with that, so things have started to become a little bit simpler, that now you just have to get a few more terms and you can write down the final expression of entropy. Remember, we after all this while we have just used the non-relativistic limit. We have not actually denied any of the conditions that were given. So we have used non-relativistic limit, and also you have used t is very large limit. Okay, t is very high, so that your z or fugality, that is e to the power of beta mu, is very small. This limit has been used successfully, and also this is taken for 3D fermions as a system. So all these conditions are satisfied and these things are derived. Now to get to entropy, you know the general value of entropy goes like Ts equal to U plus PV minus mu n. Okay, and so basically you know that to get to entropy you have to also get this energy, internal energy total, that is P, and also this P into that is U, and this P into V is there, that is the volume into pressure. That part you also have to know. And finally mu times n. So you have to also have to know the value of mu. So for all these things we also need to calculate what is the energy per number of particles. That means what is capital U, total energy, divided by total number of particles. This is easy because you just have to readjust the term so that you divide in both the denominator and numerator by volume. So this just becomes U by V by N by V, that is your small uv by rho. Okay, so because you have already derived the expressions of uv and rho, you can just directly put that value so that you get the ultimate expression of u subscript n. So let us do that. First of all, uv was here, this part, so we have to replace 2 pi z by c naught cube beta, then the other part. So this is 2 pi z by c naught cube beta into gamma 5 by 2 into 1 minus z to the power 2 to the power of 5 by 2. Okay, and then numerator in the denominator you have the expression of rho also calculated here. So you just put this expression 1 by c naught cube into 2 pi z. So this is 2 pi z by c naught cube, then gamma 3 by 2 1 minus z by 2 to the power of 3 by 2. This is 2 pi z and 2 pi z cancels out. This c naught cube and c naught cube also cancels out. So you are left with 1 by beta. Now you know the drill here that your gamma function behaves like, if you have gamma n plus 1, you can write it like n gamma n. Okay. And also you know that gamma n plus 1 can also be written as n factorial. This is the standard expressions or values known for gamma function. We don't need to derive it especially. So this is a known formula. So if that is true, then gamma 5 by 2 is nothing but gamma of 1 plus 3 by 2. So you can express it like gamma n plus 1, right, where n value is 3 by 2. So if that is the case, just apply this one, that n plus 1 gives you n gamma n. So you get, here n is 3 by 2, so you get 3 by 2 n and then gamma of 3 by 2. And the lower 3 by 2 remains as it is, so that you can cancel both of them together. These two are cancelled out. And also you are left with 1 minus z to the power of 2 to the power 5 by 2. And for the denominator, you take it up in the numerator by just taking a inverse or minus 1 sign. Now again, there is this time has come where you have to utilize the expression or the condition of t very large, or hence z dot fugality is very small. That means this second part, the second term in this expression 1 minus sum to the power inverse is actually much smaller than 1. So you can directly use the binomial approximation and you can approximate the whole thing. First of all, it is 3 by 2 beta. Then it was 1 minus z by 2 to the power of 5 by 2. And the second term can be binomially approximated as 1 minus and minus 1 makes it plus 1 divided by into z plus z 2 to the power of 3 by 2. So this is actually by using binomial approximation, and this is also only valid because we have this condition of z very small because of high temperature limit. So once that is done, just directly multiply these two terms. So you get 3 by 2 beta, just multiply straightforward, to the power of 3 by 2 minus z by 2 to the power of 5 by 2 minus z squared divided by to the power 3 by 2 and 5 by 2. If you multiply, you get 8 by 2 or 4, right? Sorry, this is 2. Alright, so this is done. Now you see here that there is one another thing you have to keep in mind, that your z is actually given to be very very small because temperature is very high. So if z is very small, then compared to z square become even smaller, because you know, for general numbers, right? Because if you have a number of 1/3, so it is basically much smaller than 1. Now if you take 1/3 square, that makes it 1 by 9, which is even smaller than 1. So basically, compared to the quantity itself, the square of the quantity will be even smaller. So we can ignore it under the condition that z is very small. So this ignore this z square term, ignore, because z squared is very small and can be ignored. So this is what is known to be taking only the leading order terms. That means even if z is small, if you have to take the contribution from z, you will only prefer to write down what is the leading order form of the function. So we only take the leading order in z. That's why you take up to z to the power 1, and z square and the other higher order terms are ignored. So it is just 3 by 2 beta and then 1 plus your z by 2 to the power of 3 by 2 into 1 minus, so it is just 3 by 2 plus 1 is 5 by 2, so this is just 1 minus half, so it is 3 by 2 beta 1 plus z by 2 into 2 to the power of 3 by 2, which is your 3 by 2 beta to 1 plus z by 2 to the power of 5 by 2. Okay, so this is just 3 by 2 beta plus 3z by 2 to the power 5 by 2 and 1, if you multiply, this is just 2 to the power of 7 by 2 into beta. So this is basically your root over 2 to the power of 7. That means this is basically root over 2 times 6 into root over 2. That makes it 8, I think. 8 into root over of 2. Okay. So your final expression of un becomes just 3 by 2 beta plus 3z by 8 root over 2 into beta. Okay. Or in other terms, 3 by 2 beta, if you take common, it is just 1 by 1 plus z by 4 root over of 2. So this is your energy per particle. This is also simplified. And now you are only left with this PV and mu part. So let us get to PV. It is very easy because you know for any gas, quantum or classical, this formula is valid, that PV equal to 2/3 times the total internal energy, that is 2U by 3. So you know that total U is basically small un times capital N, number of particles times energy per particle. So because you have just derived the expression of un on the top, so you will just plug in that expression and you get 3 by 2 beta to 1 plus z by 4 root over of 2. So this is just 3 and 3 cancels out, 2 and 2 cancels out. So you get PV equal to n by beta into 1 plus z by 4 root over of 2. So this is your expression of PV. So these things are done very easily, and I think now you are left with just z. You have to get the value of I think mu. So that is the last part, and then we will directly go to the value of the entropy. So basically what parts we have already obtained, let us check out. So basically we have obtained PV and we have obtained un. Then we have this expression of rho also. Rho is here, and also we have expression of uv. Okay, so in the expression of uv you have also that, and so basically let us, it is we can also simplify these terms a bit, because ultimately we have to utilize the expression of the condition that z is very small, and we only have to retain up to the leading order that is mentioned in the question, right? So if you just retain up to leading order in z, because z is very small when t is very high. So to do that, you see that for the second term, for the first term it is z times 1, that means just z, but for the second term you get z into z, that makes it z squared. But we just already did for the last un part that your if z is very small, then z square is even smaller, and you can easily ignore that and keep only up to the single power of z. So if you approximate this uv in under that norms, you just get 2 pi z. The first term only retains and the second term is actually ignored under the condition z very small. So you just get this part, 2 pi z by c naught cube beta 3 by 2 gamma 5 by 2, and you can replace a value of gamma 5 by 2, which is nothing but 3 by 2 gamma 3 by 2, and then 3 by gamma 3 by 2 again you can express it by something else, and you can finally get the idea that under this condition that z is very large, your uv becomes up to the first leading order is 2 pi z by c naught cube beta into gamma 5 by 2, where 5 by 2 gamma 5 by 2 is just 3 by 2 gamma 3 by 2, and again this gamma 3 by 2 can be written as half into gamma half, again the same formula, n plus 1 gamma n plus 1 equal to n gamma n, and finally you know that gamma half is root over of pi. So this is this thing. So your uv is just it is multiplied by 2 pi z by c naught cube beta into 3 root over of pi by 4. So this 2 and 4 cancels out and remains a 2 in the denominator. So this is just pi z by C naught cube beta into 3 by 2 to root over of pi. So this is your UV. Okay, and if that is your UV, so then the last thing that remains is just your value of in by V. In by V was your rho. So let us also approximate that under the condition that Z is very small, so we only have to take the leading order. So basically similar thing, we will only retain the first part, and the second term, because it is in Z square, so we will ignore that. So it just becomes 1 by C naught cube 2 pi Z into gamma 3 by 2. So let us write down. So sorry, it was, what was it, 2 pi Z by C naught cube into gamma 3 by 2. Gamma 3 by 2. So you can replace gamma 3 by 2 by half gamma half, that is root over pi by 2. So this is just C naught cube into root over pi by 2. So this 2 and 2 cancels out. So your rho becomes pi. So yeah, your rho becomes pi to the power of this half plus 1. That means pi to the power of 3 by 2 into Z by C naught cube. So this is your value of rho. Then because this has an expression of C naught cube, and you can just replace the value of C naught cube so that you can get all the other terms, because C naught was your thermal wavelength. So the expression goes like 2 beta pi square h cut squared by m to the power of half. So if you just slightly modify terms a bit, so you'll get this, because let us not forget what was your un. So now you have to play around with the terms a little bit so that you can express one term in terms of other term. So remember your this un, that is the energy per particle, only had leading order up to single power of z. Sorry, only had quantities in single power of z. It had no z square or other terms. So if you are asked to only retain up to the leading order, then you just ignore the second term as well, because z is very very small. So only leading order just becomes 3 by 2 beta. Okay, 3 by 2 beta. So un up to the leading order becomes up to leading order, and under the condition that z very small, so it just becomes 3 by 2 beta. Okay, and this is your basically your u by n. So if that is true, then you just express your beta by this beta by 3 by 2 un, or it is just 3n by 2u. So you just have replaced your beta in terms of u and n. So we got that beta equal to 3n by 2u, and let us not forget that this is all done under the condition z very small, and you have only up to leading order you have to retain. So if that is true, then this beta is getting replaced by 2u pi square h cut squared by m to the power of half. This u and u cancels out. So this is just 3 pi squared h cut squared divided by m, and then u and by n becomes u subscript n, that is the energy. Or also let us not do that, let us retain is as it is. So it is basically to n divided by total energy u to the power of half. This is your thermal de Broglie wavelength C naught. So once that is done, you can just replace C naught in any of the terms over there. That is the, let's say, the expression of this rho. We need to replace the value of C naught. So what do you do is that your n by v is equal to pi to the power of 3 by 2 into z into 1 by C naught cube, which makes it 1 by C naught cube means m u to the power of 3 by 2 divided by this 3 pi square h cut squared n to the power of 3 by 2. So again, when we just simplify the terms, you get this pi to the power 3 by 2 is basically z pi to the power 3 by 2 into m to the power 3 by 2 u to the power of 3 by 2. I am just breaking up the terms so that it is easy for us to see what are the terms here. So this is the 3 to the power 3 by 2 means this is 3 to the power of 3. And this is pi square to the power 3 by 2, which makes it pi to the power of 3 by 2. Again, h cut square to the power 3 by 2 is just h cut cube. Sorry, this is just pi cube then. Pi square into 3 by 2 makes it just pi cube. Or you can just express it like pi square to the power 3 by 2. And then it is h cut cube, and then this is just again into the power of 3 by 2. Then you see that some parts actually cancelled out some terms. So what are those terms? First of all, z remains as it is. Then this pi squared to the power 3 by 2 and pi to the power 3 by 2, they cancel out or adjust out with each other, and that makes it this whole mu to the power 3 by 2. Let us not forget what was on the denominator. It was just 3 to the power root over 3 means 3 to the power 3 by 2. And then this pi to the power 3 by 2 is remaining. So it is just, let us write it by pi. Then h cut squared, because we need to take the ultimate power as 3 by 2. So we again readjust the terms like this. So this is your n by v. Now you see, the trick is that we have obtained the value of n by v, but actually we are looking for the value of z so that we can convert from it the value of z. So your z becomes n by v into 3 pi squared 3 pi h cut squared into n divided by mu to the power of 3 by 2. So this is just your z. So you also know that z is nothing but your fugality, that is e to the power of beta into chemical potential. So if that is true, then e to the power beta mu is equal to this whole thing. And we can just express what is the value of mu then, because mu will be the log will be taken here, ln. And there will be this 1 by beta factor. So this is just 1 by beta and then ln of this whole thing. So we are gradually approaching the main solution. So this is just divided by mu to the power of 3 by 2. So this is your value of the chemical potential obtained for the limit of z very small or temperature very large, and only leading order terms are taken. So almost all the parts are separately done. So now we combine the whole thing up and get the expression of entropy. 1 second. So I was basically kind of in the middle of a derivation. So I was solving the last week's assignment that I was solving in the last class. I think it was last week. But one derivation was left that I could not solve or complete because it was a lengthy derivation. So I was just finishing off that part. And after that I am going to just, because this week's assignment are not that lengthy. So that is luckily enough for us that we can finish that in time. So basically we have already separately calculated out all the different terms that are needed to get our entropy in the high temperature limit for non-relativistic fermions in 3 dimension. And we have got all the separate terms of this chemical potential mu, and then this n by v energy per volume, sorry, the particle density. Then we have obtained the values of these, what are these? All the other terms like the volume density of energy, and then the term of P into V, all the terms that are needed for getting the expression of actually T into S, where the entropy lies. So Ts is basically, we know that this is our P plus UV, PV minus U plus PV minus mu N. Now you see that we have already obtained the value of U. Where we have got it? So let us go back here. So this is your UV, advance your u. Yeah, this is the case. So basically this was your u by n, that means u subscript n, and this was when we are to take only the leading order, so we ignore the second term in z. So we just get u by n equal to 3 by 2 beta, and from there we obtain that our u will be just 3 into capital N by 2 into beta. So this is your expression. This is just u equal to 3n by 2 beta. So that part is known. Let us just substitute that here. So your u is 3n by 2 beta, and also you have known the derived the expression of p times v, right? So if your p and v, p into v are done, so this is just n by beta, and then the second term has z. But again, if you have to just take the leading order, if just leading order is taken, because your z is very small, so you can ignore the other terms. So the leading order is just the initial constant term, right? So that makes the whole thing very simple. So this is just pv equal to n by beta. Again, replace that here. This is just n by beta. Finally, we are only left with mu times n. So we have already derived the value of mu, and here you see there is no limit that has to be taken any further, because it is already in terms of some quantity that does not have z, right? So you do not have to take the limit in z. So you just directly multiply this expression by n. So this is n by beta, then ln of n by v into 3 pi square, sorry, not pi square, this is pi h cut square into n by m. Now you also have to replace the value of u here, because here you replaced your u by 3n by 2 beta, right? So you also need to do the same thing here. So you replace here 3n by 2 beta. So this n, 3 and 3 cancels out, and you will see that this n and n also cancels out. So what will be the final expression? So this will, first of all, this 3n plus 3n by 2 beta plus n by beta minus n by beta ln of n by v into pi h cut squared into 2 will be in the numerator again, because this 2 comes up, and this is just m that is left in the denominator, and another beta will come on top. Okay, so this is your 2 beta pi h cut square divided by m. Sorry, I forgot one power here. There is 3 by 2 that I forgot to write. So this is just 3 by 2. Alright. So if that is the case, then finally we have reached our final answer after all this derivation, that your s is just okay, so you can simplify it a bit further so that things become even simpler. And for that, what we can do is that let us, because this so let's add this thing up. So this gets you 5n by 2 beta. I think this is 2 times, so this is 5n by 2 beta. And when you take this t to the denominator, so this is the 5n by 2t beta minus then n by t times beta ln of n by v. Then this was sorry, I re-expressed the terms in another format, but actually in the options that are given to you in the MCQ question, that was given in terms of the other format. So we will just retain the earlier term, that was this 3 pi n h cut square divided by m into total internal energy u to the power of 3 by 2. We will see why this I have done. So ultimately this t by t and beta gives you 1, because t is equal beta equal to 1 by t. So this cancels out, and you get 5n by 2 minus n ln n by v into 3 pi n h cut squared divided by u m. So now you will look at if you look at the options, you get to see that there is a s that is involved in the term. So just to match our answer to the given options, you can also include a 8 constant, some variable term or constant, we don't know. We just multiply it by some a squared, so that it makes it, because ultimately it is outside 3 by 2. So you are basically multiplying the denominator by a cube. So to adjust that, because there is no a cube from previously, So you adjust, to adjust that you also multiply your a cube in the numerator. So this is the final expression, and the entropy is equal to, this is also in the expression given like this, instead of n you can also write it like rho times v, right? So you just do that, because you know rho equal to n by v, so you can replace n divide equal to v times rho. So that is what we have done here. So this 5 rho by 2 minus rho into ln into this a cube n by v 3n pi squared divided by u ma squared to the power of 3 by 2. This is the whole bracket. So this is your final expression of entropy. You can just go ahead and check whether this matches with your given answer in the MCQ options. And remember that this we have derived for 3D fermions or Fermi gas in non-relativistic limit, or in short NR limit, and under the condition that the temperature is very high, and that gives you the Z, that is e to the power beta mu will be very small, and only up to leading order of magnitude is taken, only retained up to leading order, and you get this term. So you can just go ahead and check that actually this is your answer that was already given in the question solutions. So you see that the same answer they have also obtained, right? It matches. So basically our this thing is done, that calculation or derivation.
Madam,
Yeah.
I think the answer has the plus sign, but in our what we have been doing, it was minus. Right?
It was minus sign. Just let me check.
Yeah, in the solution that you are providing us, that's coming minus sign, but there in the
Just let me see whether I have done any mistake in between.
okay.
Yeah, there is this minus sign, but the formula is right, u plus vv minus mu n. I can't go.
Ma'am, in some textbook it is minus sign. I referred that.
Oh, so is the, so it maybe the option is actually wrong, or what? There can be some minus sign problem. I don't know, because this is what is coming out, because
Yeah,
I
this seemed to be correct.
yeah. So that may happen that there is some sign mistake in the option, okay? Because that the main thing we started with, this ts equal to u plus pv minus mu, and this is right, okay? There is no problem doubt with that. So we just have to take out and derive the individual terms, so that we can ultimately get down to this term of entropy. So until and unless I have done, so basically this cannot happen, because in every other term there is no minus sign problem. So this is, I think, the final format should be. But anyway, if you are given the options, you can see that in the options, if the minus sign is not matching, otherwise you can just look at the other things, because in every option you have this plus sign, but looking at the other terms you can get to see that this 5 rho by 2 and this rho ln this thing, this actually matches with our answer instead of this sign. So we just take out the answer as our final answer. And okay, so hopefully this part is done. And also I left one other question from the last assignment thing. Just let me go back. What was the question? Because that is actually related to this part, so I do not need to, I suppose I do not need to solve that by total from the beginning, because what was given is question number 6. You can see that in question number 6 it is given that in question 5 the next leading contribution to entropy at high temperature is then there is a big much like longer expression that is given. But if you just look at the expression, you will see that we have already derived up to the leading order, right? Basically, I think if I remember right, then the this was our final expression, a cube n by v. Yeah, so this instead of this sign, so this is ignore that. So if this is minus sign, then this is 5 rho by 2 and rho ln a cube n by v. Sorry, this was not there is three part here, so this might be, so from this question, option number A or option number B, in between these two, So option number A is also not correct. Option number B, sorry, I did not look at the entire expression from earlier. So this is just simple because you already derived this part, right? With this minus sign, plus sign should be replaced by minus, but you got 5 row by 2 and this row into some this part, and only there is one extra term over here in this question because you are asked that you have to also include the next leading contribution to entropy under the same high temperature limit. That means from where the change begins is that up to this part it is fine, up to the second term we have already obtained from the derivation. Only for the last part you have also the term you have ignored in the in our derivation here, you have now to include you now have to include those parts to actually get the third term. Like say I can just point it out to you and then you can get it by yourself. That like for example in this case P into V, there we just got in by beta and then 1 plus z plus 4 to the power 4 root over 2, but we ignored completely the second part, right? And we only got this in by beta part. And also for un case you also obtained you only retained this first part and ignored the second part. So maybe if you retain those parts and recalculate, just there will be an extra added term and that will be your next contribution, I mean after the leading order. So I think I will not solve that again separately because this is connected to this question also. So just let us continue with this week's assignment now, because not this week because that deadline has already gone, but I'll solve that to you in this tutorial. And so basically the most of the part that was actually I was telling you that it will be a lengthy calculation, it is already done, and how much time we have left is close to 1 hour. It is 40-50 minutes is left. So I think within that time I can finish up this week's part that I have planned to do. So let us go back to our question set now. Okay, so this week's part is basically like on topic is on the degeneracy pressure and this ultra relativistic limits, this thing. So but relatively this calculations are not very much longer derivation type like we had in the last assignment. So it will be fun to solve it. Let us understand and start from question number 1. So your question number 1 is telling you that the question is the degeneracy pressure of an ultra relativistic Fermi gas in 3 dimensions may be written as rho equal to P equal to rho to the power of n, and you have to calculate the value of n. Now I hope you are already familiar with the formula directly from the lecture itself, but instead of that it will be nice to actually know how the formula comes, because you know that professor had mentioned that this kind of a formula is known as a polytrope equation. Polytrope, because this equation is actually making a relation between the pressure P and the density rho, and there is a power law type of a relation. Density to the power of n power is there. So this is a polytrope equation for the gas, and the limits are that you have an ultra relativistic limit, and if you are familiar with ultra relativistic limit, that is basically you know that there is this relativistic limit, then there is non-relativistic limit, right? And in similar way you can also have ultra relativistic limit. So let me choose a separate page so that I can start explaining. Yeah, so this is how, which week will be, it will be probably week 5, I don't remember. This assignment is from week 5, I guess. So the question number 1 tells you that you have an ultra relativistic limit. So ultra. So in short, I prefer to write it as UR limit, just for so that I do not have to write it again and again. But this is UR or ultra relativistic limit, and the other limit you are familiar with, that was also mentioned in the last question, that was your non-relativistic limit. So first of all, understand the difference between the limits, because that is what you need to apply. In different questions you will be given the limits as different. It may be the same problem, but depending on the limit that you have to apply, the question of and the solution will be different. So for ultra relativistic limit, the idea is that the system you are given is moving with a velocity that is actually much greater than the velocity of light itself. So if you want to express it, you can, the condition can be expressed like your momentum of the system times light's velocity is much greater than m times c squared. So how it is expressed is that c is basically the velocity of light, and your momentum of the system is here p. So p times c give you a dimension of energy, and mc square is also the rest mass energy dimension. So alternativistic limit condition gives you or tells you that this p times c is much greater than the rest mass energy mc square. And on the other hand, the non-relativistic limit is when your system is moving in a velocity that is actually much smaller than the velocity of light, which is actually the idea of most of our like commonly known objects that are all in non-relativistic limit. So in this case, the limiting condition will be p times c is much smaller than mc squared. So basically nothing, it tells you nothing but just p is much greater than mc, or here p is much smaller than mc. That means the momentum that you get from the system is much greater than the momentum associated with the speed of light, or either it is much smaller than the momentum associated with the speed of light. So this is your idea of the relativistic, non-relativistic and ultra-relativistic limits. So in this question you have to get the application of this limit itself, the first limit. And so basically you are asked to get the expression of p equal to rho to the power of n, and you have to get what is the value of n, where pressure is p and rho is just nothing but the particle density, or n by v. Okay, so what we can do is, first of all, let us start with the expression of pressure, that is the left hand side. So what is pressure? Pressure, you know that it is also mentioned in the lecture, so you can go back how this is coming. So pressure can be expressed as del S del V divided by del S del U, or directly use the value that is given in the lecture, so that we don't have to do the derivation from the starting, because this is already known to you. So this is 2 by beta V into j equal to 1 to infinity, then logarithm of 1 plus to the power of minus beta epsilon j e to the power of beta mu. So let me tell you that this is precisely given for the Fermi gas, and this is the degeneracy pressure of the Fermi gas, or this P expression that is here. This is a Fermi gas and this is the degeneracy pressure. And this is the standard expression that is already given in the lecture. You can look at that if you do not remember. But this is the expression, and this epsilon j, this is basically your energy for the jth level, you can say. In the total expression of energy, you know that the energy in general can be expressed as E equal to root over of p square c square plus m square c to the power of 4. That means if you express p in terms of h cut into k, where k is the wave vector, then you can write it as h cut square c squared k squared plus rest mass energy mc squared whole square. So this is your epsilon j in general. So this is your general expression of energy, total energy. And right now no limit has been put on this energy. If you use the non-relativistic limit, then the value will be different, and if you use the ultra-relativistic limit, then the value will be something else. But right now this is a general expression. And now let us go back to the value of the degeneracy pressure P. P was your this whole thing 2 by beta V into this summation. So we need to simplify this term. Okay, how to simplify this term? So you need to first of all use a limiting condition, that is your very crucial. That limiting condition is you have to apply temperature very low or T tends to 0. Or in other words, you can say this means that beta, that is 1 by temperature going to infinity. And you may ask that why this kind of a limit has to be taken, because in the question itself there was no mention of this limit separately, right? But this is the idea of degeneracy pressure, that whenever you are asked to ask the idea of degeneracy pressure, you have to know that it is actually meant in the question that the temperature is very low, because degeneracy pressure is something that is related to a quantum mechanical effect. It comes because of the Pauli exclusion principle of the fermions. So It is because of the Pauli exclusion principle of fermions, which are quantum particles. That actually gives rise to degeneracy pressure. Let us write it as P, and since it's a purely quantum effect, it's best realized when the temperature is very small or tending to zero, because you know that at such low temperature all the classical effects that are dominant in other cases actually vanishes. So at this low temperature all classical effects are no more dominant, or almost they vanishes, or no more dominant, and therefore you get the purely quantum effect of the degeneracy pressure, that is P. So that is why you choose to, or you prefer to, whenever you asked about degeneracy pressure, you actually by default take the T tends to 0 limit, or in other terms beta tending to infinity limit, right? So that is what we need to use in the expression here. You need to simplify this summation by using that limit. So this was your P equal to 2 by V. Now the limit is here, T tends to 0 means beta tends to infinity, and you had a 1 by beta also, so let us put it inside the limit, 1 by beta, and then log of 1 plus e to the power of minus beta epsilon j and to the power of beta of mu. So how to do that? Basically you see that if you just directly put beta is infinity, then it is 1 by infinity, and then it does not give you any proper solution. So you just need to apply the L'Hospital rule, because this log of 1 plus e to the power minus infinity is 0. So basically this is log of 1 plus 0 divided by beta is infinity, and you know that log 1 is 0. So this is 0 by infinity term, which is invalid. Okay, so you need to apply the L'Hospital rule to solve the limit. So you just take derivative with respect to beta on both the numerator and denominator. So you get, first of all, log becomes 1 by 1 plus e to the power of minus beta epsilon j into the power of beta mu, and then if you further take the derivative with respect to beta, so of this part, so then it is 0 plus e to the power of, let's say, beta mu minus epsilon j, and then again one other derivative with respect to beta gives you mu minus epsilon j, this thing. This is the entire derivative with respect to beta on the numerator, and on the denominator it is just simple beta, so it just makes it simple 1. Now you see what is the value. So this is just after the limit. So you are still on the limit of beta tending to infinity. So you get limit beta tending to infinity mu minus epsilon j e to the power of beta mu minus epsilon j divided by 1 plus e to the power of beta mu minus epsilon j. Now you see that here in this case, if you plug in the value of, what can I say, am I missing something? E to the power of infinity is mu greater than, just 1 second, I have confused it a bit. Yeah, I have to another time take the derivative, I think, because again if you put the directly value of the limit, so it gives you an invalid format. So let us take one more derivative, the L'Hospital rule. So it is just mu minus epsilon j, and because there will be another term coming from the derivative itself, so this is mu minus epsilon j whole square e to the power beta mu minus epsilon j. Then here in the denominator this is just 0 plus mu minus epsilon j into e to the power of beta mu minus epsilon j, and to the front beta tending to infinity limit. So what it tells you, that finally you are left with just this term, that limit beta tending to infinity, this cancels out, so this is mu minus epsilon j, and this part also cancels out. So ultimately this is in a valid format, and you do not need to uh, uh, take the use of any limit, and you get a valid format. So the final answer is just 2 by beta mu minus epsilon j, right? But also here in this case you will follow that if your mu was, let's say if your mu was greater than, not greater than, if your, let's say this condition is taken that your mu is less than epsilon j. Okay, so what will happen then? So then mu minus epsilon j will be negative, right? So then this part that you have just simply cancelled out from the numerator and denominator would not have been so easy, because then you would get e to the power of beta mu minus epsilon j will make it e to the power some minus, because this mu minus epsilon j is coming as negative, so this is minus beta times some this term divided by, just 1 second. So divided by, this is e to the power of, again there would be some e to the power of minus beta times some quantity, because this part will be then negative, and if that was negative, so your limiting condition is beta tending to infinity. So what does it give you is that e to the power of minus some infinity into some constant, and e to the power minus some infinity times some constant. So that basically gives you e to the power minus infinity, you know, is 0. So this is 0 by 0, which is again an invalid format, right? So to actually get this into a valid format and get this final expression like this, you have to strictly apply the condition that your mu should be always greater than epsilon j, so that your mu minus epsilon j is greater than 0, and you do not end up with the 0 by 0 type of an invalid format in the limiting condition. Okay, so this is your final condition that you need to remember, that your final degeneracy pressure when the temperature is very low for the fermions is just 2 by v. Then your summation, that was summation over j from 1 to infinity. So the initial summation, let's say, was from I missed out the summation in the last line. So it was j from 1 to infinity, right? So we needed to put the summation over here, that j from 1 to infinity. Anyway, because when we are taking the limit, the summation will just come at outside, so we can ignore that. And finally, in the final expression, we'll again return back the summation. Okay, so just correct that part. So this was your j equal to 1 to infinity, but now you cannot just say j equal to 1 to infinity, because you have also to apply this limiting condition. And how is that utilized? So that is taken as mu is greater than epsilon j in the limit of summation, in the summation index itself, and then mu minus epsilon j. Now also you remember this fact that you are applying t tending to 0 limit, because you need to calculate the degeneracy pressure, and you know that when the temperature is almost close to 0, your chemical potential is nothing but your mu f, which is your basically the Fermi level energy, right? You know that when the temperature is very small, then this chemical potential value is at the Fermi level value, and then hence you can replace it by mu subscript f, which actually denotes the Fermi level energy and the chemical potential corresponding to that. So finally, after applying all the conditions and maintaining all the valid formats, your idea of degeneracy pressure for the fermions in the ultra relativistic limit is, so we have not yet applied the ultra relativistic limit. So basically this is just the idea of degeneracy pressure for fermions when the temperature is tending to 0. So instead of mu, we'll put just mu f, and obviously this mu f will be greater than epsilon j, and based on that the summation over j should be taken, and then again it is mu f minus epsilon j. Up to this is fine. Now you need to apply the condition of, I think, the ultra relativistic limit that I was talking about. So right after, just apply the ultra relativistic limit. So the energy values will be depending on that, how that will change. So the ultra relativistic limit, we know, we have discussed earlier that this is just P is much greater than the m into C. In this case, because you are at t tending to 0, that means everything everything you take is just near the Fermi level. Just like that, at t tends to 0 you replaced mu by mu f. Similarly, you can also replace p by pf, the Fermi level momentum, when you are close to 0. So basically this tells you that your pf is much greater than mc, right? And hence if that is true, that means your h cut kf is also much greater than mc. Just p equal to h cut k, so h cut kf is also much greater than m into c. Now your total Fermi level energy ef in the general formula was supposed to be c squared h cut squared kf squared plus m squared to the power of 4. But now because your this h cut kf is much greater than mc, so you can easily approximate this thing under this condition that h cut kf is much greater than mc, is just the second term will be ignored and that this last part, this first term will be retained. So your ef just approximated to c h cut kf, as simple as that. So this is under the ultra relativistic limit. Okay, this is approximated like that. And similarly, because your epsilon j was what? Your epsilon j was also the general expression of the energy h cut square k square c square plus m square c to the power 4, where this value of k will have an indexing of j depending on which j value is taken, which level is taken, but maintaining the condition that your mu f will be greater than your epsilon j, or in other words, every epsilon j level you take has to be below your Fermi level. So this is your condition for t tending to 0 limit, that you already checked that how it is actually obtained. So all the Fermi energy levels that are below the Fermi level are taken, and the general expression is this. Again, when you apply the ultra relativistic limit, that is the UR limit, which tells you that your h cut k is actually much greater than the m into c. So this again tells you that this is this thing, and hence epsilon j is approximated to h cut k into c. Okay, so where k is basically the wave vector corresponding to the energy level of epsilon j or the jth level. So now after knowing that, you can just replace these things in the degeneracy pressure expression, that was 2 by v summation over mu f greater than epsilon j, mu f minus epsilon j. So just replace this part and this part. So I already told you that mu f is also equal to epsilon f. Sometimes it is written as ef, which is not epsilon f, it's ef, that means the Fermi level energy. And mu f is also the chemical potential, which is equal to the Fermi level energy. So they are basically the same notation. So just replace that. This is 2 by v, and then what was our formula? 2 by v, and then sum over this thing, mu s greater than epsilon j. Then mu f was just h cut kfc minus epsilon j is h cut k into c, right? So after that we can just go ahead and solving this summation part. So you know the drill, that in this kind of a summation you just convert it into an integration, considering that the summation is actually very closely compiled together. That means in each small part, if you divide the summation in small parts, then each part is so small that it can almost be considered as a continuous case, and therefore you can convert this discrete summation into a continuous integration, just like you know that you can do in momentum space, right? So in doing that, we have to, this is 2 by v. So basically in every momentum space small part, if you write this k as 2 pi by l, this is a conversion between real space l and momentum space k. So then your v, so to get your convert your summation into integration, you have to multiply this whole thing by, the summation to integration you have to convert. So you have to multiply by v divided by 2 pi whole cube, and then your d cube k. So this is the basic drill that you have to apply, and that's how you convert the discrete summation into continuous integration. And why that is coming, because you know that this k is equal to 2 pi by L. So once you take the each small quantity that is in momentum space, which is basically 2 pi by L, and because you have this inverted thing has to be taken 1 by volume in k space, so that is basically 1 by, because it is in 3 dimension, so of the cubic box if you consider, so this is just 1 by 2 pi by L whole cube. So this is for a cubic box in k space, where each side of the box is of 2 pi by L length. Okay, so this is just makes you L cube by 2 pi whole cube, which is nothing but L cube is V, total volume in real space, and the 2 pi cube is remaining as it is. And that's what is the prefactor in this summation to integration, that you multiply V by 2 pi cube and then take the integral of k space as d cube k. Okay, so this is the idea. I think this is already something that you are familiar with, but still I chose to explain. So this is basically the thing. So you convert, and what you get is just V by 2 pi cube. This V and V cancels out, and then you are left with this h cut kfc minus h cut kc into d cube k. Now the thing that is crucial is that you had this limiting condition on the summation, that your energy levels were all below the Fermi level. That means if you now apply this, want to retain this condition also in the k space in the integration, you do not choose the integration limit from 0 to infinity, but instead your limiting condition is from integration limits are from 0 to kf. Why that? Because 0 to infinity will not be right, because you cannot take all the energy levels. You have to stop maximum at the Fermi level energy, which is in the momentum space, the momentum of kf, right, the wave vector of kf. So that is your upper bound of the integration. So following that, your pressure is equal to 2 by 2 pi whole cube. Now just consider not solving the integration, this is simple. So this is your, first of all, this is h cut c into kf minus h cut c into k into then d cube k, you write it as 4 pi k square dk, the 3D volume element. So this is 2 by 2 pi whole cube into 4 pi is constant coming outside, and then you just term by term integrate h cut c into kf into this k square, means that makes you k cube by 3, and you apply the limit of kf to 0. Okay, and then on the second term you get to do h cut c, then there is another k, so this is k into k square means k cube. So when you integrate k cube dk, it makes it k to the power 4 by 4, which is again when taken the limit of kf to 0, right? So this is 8 pi by 8 pi cube h cut c kf to the power whole to the power 4 by 3 minus 0 is 0. So the second term is also h cut c kf to the power whole 4 by 4, 0 is 0. So this is your 1 by pi squared h cut c kf to the power 4, 12. Okay, so just look at the calculation. If I am doing wrong anywhere, just point it out. So h cut c kf to the power 4 divided by 12 pi square is your value of the degeneracy pressure under the limit of t tends to 0. But you have to express it in terms of the density of rho. So you just have to readjust the terms so that you get the ultimate expression. So this is simple. You just know the expression for rho, and how rho is calculated. Rho is basically your particle density or number of fermions per unit volume, n by v. So that is also a known condition, that it is just equal to 2 by v summation epsilon j is less than mu f. That means mu f is greater than epsilon j, that limit. And you know that below Fermi level, you are choosing all the Fermi levels that are below the Fermi level. And you know, for fermions, what happens at t tends to 0 is that up to the Fermi level, every level is occupied. So the probability of getting the fermions in any level that is below the Fermi level is always 1. So that is why you have this one term here. So this is the Fermi distribution function rule. You know that the distribution function is such that it is almost like a step function at t equal to 0. That means if this is your distribution, let's say this is your distribution and this is your, not row, let us identify it by some other, let's say this average of n, average number of particles or number of average particles in energy level j, let's say. So that you write as n average or nj average, and it is your the value is mu f or epsilon f. This is the energy axis. Okay, so this tells you that up to the, this is 1 value and this is 0 value. So this tells you that this average number of particles per energy level nj is actually value is 1 when the energy ej are all less than mu f or ef, and is equal to 0 everything above. Okay, and because in the summation limit you have this condition applied that you have to choose only the levels that are below the Fermi level, because you are at energy temperature 0, so you cannot go to higher levels. So then this inside the discrete integration summation you have the value of 1, because here this value is 1. So this is the basic idea, and this is because of the limit t tends to 0 anyway. So this is 2 by v, and then yeah, so this is basically you have to again convert the summation into integration. How to do that? To do that you just use the same drill, that it is multiply by v by 2 pi cube, and then because there is only 1, so you just multiply 1 by d cube k, which is 4 pi k square dk, and take the limiting case at 0 to kf. So this is simple, 2 by 8 pi cube into 4 pi into this k square dk is basically k cube by 3, which is under the limit k to the power kf to the power cube by 3. So this is your 2 and 4 is 8, 8 and 8 cancels out. This is your kf cube pi squared by 3 is your rho. And if you want to now convert, because in this case you have p in the other side you have this kf, so you have to convert the kf in terms of rho. Now that is simple because you know this expression. So let us convert kf as 3 rho by pi squared to the power of 1/3. That means your kf is going as rho to the power of 1/3. Once that is clear, just directly use this expression that p equal to h cut c kf to the power 4 by 12 pi squared. So pf equal to h cut c by 12 pi squared kf to the power 4. So you can directly put the whole thing, or you can only take the order itself to get the power. We will directly use the whole formula. So this is 3 rho by pi squared to the power of, because this is 4 and this is 1 by 3. So this makes it 4 by 3, right? So you do not need to go to the other constants because that is irrelevant. Only focus on the power of rho. So this is p goes to rho to the power of 4 by 3. So this is again a polytrope which connects your pressure and degeneracy pressure of fermions and the density of fermions, and the value of n is equal to nothing but simply 4 by 3. And remember that this is obtained under the ultra relativistic limit where the value of n is 4 by 3. So our answer to the question will be 4 by 3. And just for the sake of it, because we were talking about the different limits, so what if we had been given the question under the non-relativistic limit? So this is not given in the question, but I am just doing it extra, that if you are asked about non-relativistic limit, then simply everything else will be same, just your energy will be different under the non-relativistic limit, because you know then your p will be much smaller than m times c. So under this condition, if you use the generalized expression and simplify that, you will get that this reduces to just square by twice m. This is our simple non-relativistic limit. Under this limit, this energy value is this. So after that, you just know the value of pressure is just 2/3 times the total internal energy, right? So not pressure, P into V is basically 2/3 into total energy. So you just replace the value of energy, which is here as your P squared by twice m, Okay, so p squared by twice m was your, oh sorry, not only that, you have also to integrate the whole thing to actually collect all the levels below the Fermi level, right? So again have to do the similar integration that we had done for earlier. So how to do that is basically, because this is the total energy, right? This is for all levels epsilon j below the Fermi level, right? So to actually get all the levels, you need to take the integral for all the energy levels. That is again the integral in k space, which is simple like before. This p equal to 2/3 v, and there is another v in the top for the integration conversion. So this is 3v into v by 2 pi whole cube, and then instead of each level of wave vector k will now have an energy of h cut square k squared by twice m, because that is under the non-relativistic limit. So you take the integral over h cut square k squared by twice m, and then d cube k you write at as 4 pi k square dk, and this is up to 0 to kf, right? So this is you just ignore all the other constant terms, because we only want to know what is the term in k. After that we need to know the power, right? So ignoring all the other constant terms that are, let's say, keep inside the bracket. So this is just k square into k square dk, that means k to the power 4 dk. So when you take the integral, this is k to the power 5, and because this is the limit is kf, so kf to the power 5 by some constant by 5. Okay, other constants are inside the bracket, let us ignore that, and the power is just p goes as kf to the power of 5. And just now we obtained what is the kf in terms of rho. Kf is just rho to the power 1/3, right? Rho to the power 1/3. So yeah, this will remain the same, because this is just for the system. This is like that, under no limiting condition that was taken. So if kf is rho to the power 1/3, then simply p pressure will be going like rho to the power of 5 by 3. That means in this case your n value will be 5 by 3 for non-relativistic limit. So you can see for the same system, when you are taking the non-relativistic limit, the n value is 5 by 3, whereas when you are taking the relativistic ultra-relativistic limit, then it was 4 by 3. So this is just in general that I have derived. The second part was not asked in the question. So this is done, and let us quickly move on to the next question. It is asked, there is a certain integration is given where this function u as a function of zeta is obeying the Lane-Emden equation. This equation, if you have followed the lecture, that is mentioned in the lecture. So we will directly use the equations formula and get to solve what is this integration value from 0 to zeta 1. So let us move the blank page. Yeah, so this is your question number 2. So first of all, Lane-Emden equation, what is that? Let me write that down, equation. So this was basically 1 by zeta squared dt zeta squared du by d zeta equal to minus u cube zeta. So this is in terms of the function u zeta, given that it follows the Lane-Emden equation, right? This is given in the lecture. Now if that is there, then you can just take this zeta to the upper side. So this is zeta times u cube zeta is nothing but just readjust the terms, so that it is just equal to 1 by minus 1 by zeta d zeta squared du zeta by d zeta. So one part is done. This will be useful in the integration that is asked in the question. So what was the integrand? Just write down the question, that it was 0 to zeta 1 in the element it is given as zeta u cube zeta d zeta. So you can see why I have expressed this part like that, because that is what we have been asked to integrate. So we directly put this from the expression, because this is the named equation. So if u zeta follows the equation, then we can express zeta times e cube zeta like that. So replace by the right hand side, this is minus 1 by zeta d d zeta of zeta square. Just write it as du d zeta into d zeta. So now we got to solve the entire integration part by part. You know that part by part integration rule. I think this x dy, if you ask to integrate, then in the first term you integrate over this dy, and then for the second term there is a minus sign, then there is the derivative of the first term x, the integral of the second term, and the whole term integral. So this is basically x d, sorry, this makes you this dy integral give you y xy minus this dx into this integral again give you y. So this is basically y dx, right? So this kind of a thing, this is basically basic. I do not need to write these things, just follow the integral part by part for the two terms. So for the first term there is a minus sign, keep it outside. So minus, first of all we have to take the integral on the second term, that is this whole term, term number 2, this is the term number 1. So first of all the term number 1 is as it is, and you take the integral on the second term, which is nothing but the derivative d zeta of this function into integral of d zeta. So basically this derivative and integral will compensate each other, and you will only get the actual function, that is zeta square du d zeta left, right? And not only that, you also have to put the entire limit of integral over this thing, that is 0 to zeta 1, fine. And for the second part, because in the partial integration there is this minus sign in between, so you take the minus sign here, and what you have to do is that first you have to take this term 1's derivative with respect to zeta, which is nothing but minus 1 by zeta squared. Then you have to take the integral of the term 2, which is already taken because it will be this function into zeta squared du d zeta, and the whole thing will be inside the integral. You have to integrate it again with respect to zeta. So this is just term by term integration. Just follow it carefully and you will understand. So this zeta square and zeta square cancels out, so the things become simple because you adjust the minus signs also. So this is minus, now this is zeta into zeta square, make it just zeta into du d zeta. So if you take in the limit also to the, if you put the limit, so it makes it minus zeta 1. So let us write u prime zeta as du d zeta, the derivative with respect to zeta, let us write as u prime. So this is zeta 1, u prime zeta 1 minus 0 u prime 0. So this part also becomes 0 because it is multiplied with 0. And then the second term, because there is a minus sign from before, so this makes it minus and minus plus, and also there is a minus sign inside, so this is again making it minus. So minus, and then just du d zeta you have to integrate. So it is just du zeta d zeta makes it u as a function of zeta 1 because you have put the limit minus 0. So it tells you that it is minus zeta 1 u prime zeta 1 minus this minus u zeta 1, and then minus and minus plus, that makes it u 0. So this is your final answer if you match the options that is given. I think this is option number D, I don't, if I recollect correctly. So this is your answer to the question. Fine, this is also solved. Is there a problem? Is there a problem with the solution? Yeah, it is fine, na? Yeah. So question number 2 is then done. Question number 3 is also pretty simple. You just have to solve the integral. You have to take use of a certain function called Riemann zeta function. So this is basically, you see that I nu d nu, this is the energy density of radiation for the black body case where the temperature is T, and you have taken the frequency limit between nu to nu plus d nu. and you have to calculate the whole integral where the total function is multiplied with another nu. Okay, so this is easy. How to do that? Basically, let me solve it here again. So this is 0 to infinity nu I nu d nu. So for it you have to just know what is the expression of I nu d nu. You know that is a standard expression for black body radiation. So this is, let's say, in short, black body radiation. You know the standard expression for this from the lecture. You can also find out, or from internet, that it is nothing but 8 pi h by c squared, then nu to the power 4 into not nu to the power 4 was not there. I think I did not write down the separate expression, but anyway, so the expression is basically the energy density of radiation. So you have to know the I nu expression. I think that was 8 pi h by c squared into nu cube into 1 by h nu by kt minus 1. Okay, so let me choose a different page itself, otherwise it can be clumsy. Yeah, so that was I nu d nu. I have already written down earlier. So now if you put the integration and multiply it with another nu, so the total power of nu becomes nu to the power 4 now. So 8 pi h by c squared nu to the power 4 now d nu by e to the power of h nu by kt minus 1 0 to nu. So this is 8 pi h by c squared, and so basically here you have to make a substitution of variable so that this thing becomes easy. So you get this h nu by kt you replace by x, some other variable, redefinition of the variables. So that's why your nu is equal to just kt by h into x, or your d nu equal to kt by h into dx. But under this relation, if nu is going from 0 to infinity, x will also be going from 0 to infinity. Just nu to the power 4 is not now replaced by kt by h to the power 4 x to the power 4. This d nu makes it kt by h into dx divided by e to the power h nu by kt is e to the power x minus 1. Okay, so this is just 8 by h by c squared, then kt by h to the power of 5. This thing is constant, comes outside. This is just 0 to infinity x to the power 4 by to the power x minus 1 dx. So up to this was simple. Now only you have to solve this integration, this part. So now this integration becomes also easy once you apply the famous format of Riemann zeta function. Then the integration will be straightforward. That function formula is that if you say zeta of some k equal to, you can also express it as in summation n equal to from 1 to infinity 1 by n to the power k, and the integral form is like this, where this is 1 by k minus 1 factorial. You can find it out from any math physics book or any from internet also, that this is the formula, that then 0 to infinity x to the power k minus 1 divided by to the power x minus 1 dx. So if you put k equal to 5, then what it becomes is zeta of k is zeta of 5, then 1 by k minus 1 is 5 minus 1, that is 4 factorial, then 0 to infinity x to the power 5 minus 1 is 4 divided by to the power x minus 1 dx. So remember that this is just the integral limit you want to calculate over there. You need to substitute that. So basically this integral value will be zeta of function of 5 in 4 factorial. So replace it 8 by h by c squared kt by h to the power 5 into 4 factorial is 4 into 3 into 2 into zeta function of 5, right? So now if you multiply this 4 into 3 into 2 into 8, so that makes it total of 192 into this pi into t to the power of 5 divided by c square h to the power of 4 and zeta function of 5. Now don't mix up this k with this k, okay? So these are different. Here k is just an index that I have used. Do not confuse with that. And also here there is no k value in the option, because you know that in most part of the lecture the Boltzmann coefficient k or kb in other terms has been taken to be equal to the value of 1. So that is just for the simplicity of calculation that it is taken in 1, so that you can ignore the existence of k to be taken as 1, and this is your final answer. So this will be the option that you have to choose. Okay, so this is also done, and then associated with this thing was the next question. So that will be the next question. Let me just go back. Is that if you double the frequency and double the temperature, then the value of I nu, how that is getting changed, right? So this part is, I think, easy for you to do. You just have to put all the conditions. Let me write it here only, that where is the point here. Okay, so your I nu was basically, again you have to know this function of I nu, the dependence. So this is in nu to the power cube, and then this was this nu h nu by kt. So you have been told that you have doubled the frequency. That means from nu you have gone into, from nu you have gone to 2 nu, and double the temperature. That means for T you have to substitute by 2T. Okay, so let us do that. So the new expression, that is I nu prime, let's say nu prime is equal to 2 nu and your T prime equal to 2T. So under this condition, I of nu prime, the function is becoming 8 by h by c cube. Then this nu prime is now replacing the nu, so it is nu prime is 2 nu, so 2 nu whole cube into 1 by e to the power of h times, now it is 2 nu, divided by k times, it is now 2T, because temperature is also doubled. So this 2 and 2 cancels out each other. Ultimately the thing remains the same. So it is just the new function I nu prime equal to 8 by h by c cube, then 8 nu cube into 1 by e to the power of h nu by kt minus 1. So you basically see that the whole thing remains the same, except that there is a 8 factor that is multiplied. C squared, that's not c cube. Again, this is just constant, does not matter. So nu cube 1 by h nu by kt minus 1. So this is just 8 times your earlier function of I nu. So I nu prime, when you double both the temperature as T prime equal to 2T and nu prime equal to 2 nu, you get that this is 8 times the earlier function. So your answer will be, it is increases 8-fold. That is your right answer. Okay, so this is done. And question number 5 is just a conceptual question. I think you know that, because that is already discussed in the lecture. Also the answers are given. Because a black hole has a temperature, the reasons are that it is hot due to the gases are spinning around it. This is not true. Okay, so because this is the idea of black hole, you know, probably it is exchanging energy with the surroundings. That will be right, because if it is exchanging energy, in other terms it is at what can I say, it is exchanging energy with the surroundings, and as a result, you know, whenever a system exchanges energy with the surroundings, its temperature actually changes to actually get to the equilibrium, right? So in that sense, you can also tell that if energy is the variable quantity, it is changing the energy, then it can also have a finite temperature, because both are related. So this is right option. And the third option is also true, that it has both entropy and internal energy. That means your entropy of black hole is not equal to 0, and the total internal energy is also not equal to 0. And you know that the temperature is such that it is 1 by T equal to del S del E. So if energy and entropy are both present for the system, then there is a connection with inverse temperature. That means you can have a temperature for the black hole. And the last option, radiation from nearby and faraway stars are shining on the black hole, this is not correct. So these two will be your answer. And finally we are at the last question. Let me see how much time is there. Okay, so we have already crossed the 2-hour limit, but this last question will not take much time. So let us finish that. So the question that is asked here is that the time required for a black hole of mass of a tennis ball, that is given as 50 gram, to evaporate it is approximately, the answer you have to write down. And basically the order of the answers are different, from minus 15 plus 15, minus 21 plus 21. So you have to get the order right and then you will get the answer. So, and you have to basically deal with the evaporation of black hole with time, black hole's mass being evaporated in time. So you can directly straightforward use the formula that is given in the books, or I think present in the lecture, and solve this very easily. Or we can also choose to derive how the formula actually comes. I think that will be more conceptual, because anyway this is not a very long derivation that I will do. So here this is a black hole case, right? And you know the direct formula is something as m of t equal to m of 0 minus 3bt to the power of 1/3. This is the actual formula, where m of t is the mass of black body, or sorry, mass of black hole at some time t. M naught is the actual or initial mass to start with of the black hole, and this b is a constant, that value will be known from here, and t is again the time. So this is telling us how much the mass is changing over time for the black hole, and that is happening because the mass is getting evaporated. That's why you see that this m naught minus 3bt to the power something is there. That means whatever there was the original mass or the initial mass of the black hole, when it is evaporated with time, gradually with time the mass is getting decreased from the actual value. So that's why this equation is valid. Now we can directly get the use of this equation, put the value of 50 gram and directly get what is the time. Or alternatively, we will quickly see how this equation is coming. Is basically that in case of black hole, you actually assume that the radiation that is being emitted from the surface or the event horizon from the black hole is actually in terms of radiation energy that is being emitted, and that energy can be converted into a mass or matter in terms of a pair production process that actually gets that is actually happening in case of a black hole. So basically there is a kind of a when it is thermally radiating near the event horizon or the surface of the black hole, then there is a particle and hole pair production that is going on, and because of that the rate at which the radiation energy is getting emitted is the same rate at which the energy is emitted by the black hole, and the rate that is the in matter energy is converted into the matter by the pair production. So that is basically the main theme, that your rate of energy radiation of black hole is equal to same as the rate of mass evaporation from the black hole, and that mass is actually getting converted into energy, because mass and energy are ultimately equivalent, you know. And this energy radiation from the black hole surface or from the event horizon is similar to a black body radiation. Okay, so you get a connection with black body radiation, and you know from Stephen-Boltzmann's law of black body radiation, you know the famous formula that your energy that is getting radiated per unit time and per unit area is going as P equal to sigma T to the power of 4. So this is the energy radiated by the black body per unit area and unit time. So if you assume that the area in this black body is A, if you assume that area is A, then the energy per time that is getting radiated, energy per time that is radiated, or the rate of the energy radiation, is nothing but your sigma T to the power 4 into the area A. Okay, where T is the temperature of the black body, sigma is the Stephen-Boltzmann constant, you know this is a particular value, this is an universal constant, and this is your energy radiated per unit time in the black body radiation. Now because we are saying that the black hole is actually made to be, when it is radiating the energy, it is considered to be like a black body radiation. So in this case the rate of energy radiated per time is basically your, let's say, dE by dt, where dE energy you can express it like a rest mass energy mc square, and this is equal to, this is the black hole radiation idea you get, that this is sigma t to the power 4 into the area of the black hole. Okay, and let's say we write it as capital M, this is the mass of black hole. So this is just c square is constant, so this is c square into dm dt equal to sigma to the power 4 into a. So we have to get what is the rate of the mass getting evaporated per time, which is dm dt, is equal to, also we forgot the sign, here the sign will be negative. Why? Because the mass is getting evaporated, the mass is getting decreased, that's why the rate is negative. So this is negative sigma t to the power 4 by c square into a. Okay, so this is just minus sigma by c square into, we know we have to put some expressions, like the temperature of the black hole is known, the expression is written in the textbook, so we can use that. This is h cut c cube divided by 8 pi gm. G is I think the gravitational constant, and gm, and also the area of the black hole is also known from the textbooks, that is 16 pi g squared by c to the power 4 to m square. This is the area of black hole. Replace these values, instead of t to the power 4 you write down h cut to the power 4 c to the power 12 divided by 8 to the power 4 pi to the power 4 g to the power 4 and m to the power 4, and instead of area you write 16 pi g square by c to the power 4 m square. So now you just have to very carefully cancel out terms and see what is remaining. So I have already done, you can do it for yourself, that this is dm by dt. Now there is a m square term that comes here, which is this m square, m to the power 4 cancels out and give you a m square which comes to the left, then m square dm by dt is just equal to minus h cut c to the power 4 by 15 into 8 cube into 2 into g squared into pi. How I am getting that? Because I have just cancelled out the terms properly. So basically h cut q was below somewhere, I have missed that probably. Yeah, sigma, yeah, we have to also use the value of sigma, that I missed. So sigma is Stefan-Boltzmann constant, this is also a known value, so we have to put the value of sigma as 2 pi to the power of cube divided by 15 c square. This was not h cut cube, this was h cube, so you have to remember the difference, that this is 615 c square and h cube, and because your h cut is just h by 2 pi, so you know that the relation between h and h cut is this. So you can replace your h by h cut into 2 pi and use that in this expression, because everything here is in terms of h cut, and when you do that and you simplify terms, you will get an an expression like this. So further solving it, m square dm dt equal to minus h cut c to the power 4. If you multiply this whole thing, it is 15360 g square and pi. Okay, so let us write the constant total term on the right hand side as minus of b. So you know now the constant value of b is, in terms of all the known constant, h cut c to the power 4 by 15,360 to g squared into pi. So final expression is that m square dm dt equal to minus b, or your, if you take the integral on both sides, it is just m square dm equal to minus b dt. So what does it give you is that m cube by 3 equal to minus bt plus some constant, let's say constant is, let's say, not a, let's use some other identity. Let's use small a. This is just integration constant. Okay, so now you can clearly write down, put the integral limits and simplify. Here m cube equal to minus 3bt plus 3a. Now you can write, you know that at t equal to 0, that means at the beginning no mass has been evaporated from the black body, so it has its original mass of m naught. So you can just directly use that m naught cube equal to 0 plus 3a. That means 3a is nothing but m naught cube. So m cube equal to minus 3bt plus m naught cube. So if you take terms on one side, m minus m naught whole cube, not this thing, m cube minus m naught cube equal to minus 3bt, and your m is just m naught minus 3bt to the power 1/3. So this is your expression that I also had written earlier. This is the final derivation, how we are getting this expression. Sorry. Okay, so this is the evaporation formula of black body's mass. This is the initial mass, this is the time over which it is getting evaporated, and after that time this is the mass that is remaining after the evaporation. And the b value is already written, what is the constant value of b in terms of all other known values. Okay, so now quickly solve the question that is asked, that your initial mass of the black hole, initial mass m naught, is given equal to a tennis ball's mass, which is not in a practical sense, but let's say for the sake of the solution, consider it as a question has asked, that is at 50 gram. Okay, so this is at 50 gram. That means you have to say what is the decay time, that means when the total black hole will be evaporated. Let's say the decay time is tau. So after the total evaporation you have no mass left, right? So your final mt will be 0 equal to m naught minus 3b tau to the power 1/3. That means your 3b tau is nothing but m naught cube, and your decay time is equal to m naught cube by 3b, where you have to replace the value of b in terms of known constants. So directly use that here. So you have to know what is the time t tau after which all the mass will be evaporated from the black hole. It is m naught cube, that means 50. Instead of writing it like that, let us just first write all the terms and then we'll get to that. So let us now keep it as m naught itself, m naught cube by 3 into b. So b expression of b was h cut c to the power 4 by 15,360 into g square pi. H cut c to the power 4 by g square pi. So let us write that down. So this is h cut c to the power 4 by 15,360 d square pi. Okay, this is just m naught cube g squared divided by, so this is just 1 by, if you just adjust the constants, pi 1 0 to the power 4, h cut is h by 2 pi to 1 by pi. So this is tau equal to pi squared m naught cube g squared by h c to the power of 4 into 10 to 40. So this, if you now put the known constant values, like age is the Planck's constant, which value is the in SI units, it's this in SI units. Gravitational constant value in SI units is this, and you know the mass has been converted into SI is 50 gram to kilogram. That means 50 into 10 to the power minus 3 kg, which is also in SI. So after doing all this and putting all this thing into here, you get that tau value is basically 1.046 into 10 to the power of minus 20. Now you'll see that the question, the options that is given over there has a order of 10 to the power minus 21 as a possible option. So you can also always write this expression in terms of 10 to the power of minus 21, because you can adjust that decimal place here in the first term. So one thing is obtained, that you have successfully obtained the power that is given in the options, because in the options you had powers like 10 to the power 15, minus 15, 21 or minus 21. So clearly right after you have solved for the power, you do not need to bother about what is the constant term in the before of that, in the front of that, but you have already have your option or answer, that is it is 10 to the power minus 21 seconds, right? Now this constant part, if you are really critical about it, or like you want to match it with the options, then I think it is also a mistake over here in the question, because I followed in the lecture there was one pi factor missing. Okay, so there is one pi factor that they missed in the expression, and because of that their formula had given answer of, let's say, this, if you just this 0.1046, this 4 factor, if you divide it further by pi, or let's say you divide this whole option that you have obtained, our answer was 1.046 into the power of minus 20 second. If you divide this whole thing by another extra factor of pi, you will get the answer comes exactly as some 3.33 into 10 to the power of minus 21 second. So basically I think there is this pi factor that was misplaced in the calculation in the lecture. Because of that the 4 factor value is actually changing, but you do not need to be bothered about that, because ultimately we have reached our final aim, that the order of the time 10 to the power minus 21 is your final answer, because this is such a small time, so it does not matter what is the 4 factor for the decimal place, right? So but unless nonetheless if you want to match the answer, then this is how that is obtained. But our formula is correct, that this formula of this tau decay time or this value of b, these formulas are correct. You can also check it with another textbook that is or available anything in the internet. So this is our correct formula, and this is the formula of black hole's mass radius.
Ma'am, m0 cube minus 3bt whole to the power of another, no?
Yeah.
Oh. Okay.
So you'll see in the lecture video, they I think missed the pi factor. I'll tell you where. They missed it in the expression of b. When they calculated, when they separated out the factor of b, so they actually, this pi was in the denominator form that we have in our form, but in the lecture I think they missed this pi, and because of that the answer, the 4 factor value actually changed, but eventually the order is getting us to the right order of 10 to the power minus 21. So anyway, the answer has been chosen. So you get to see what is the answer of the final question is this. So even after not looking at the 4 factor, you can just directly check the order 10 to the power minus 21 and know this is the right answer. And if you really want to critically look at the order, then I told you why this order is coming. So 3.36 is basically some factors, some constant factors, I think higher order if you take, then 3.33 or 3.36 is exactly the same. So it does not really matter. So this is all. I think our time is also up for this class, and so we'll be starting for the next class in the next tutorial. That is also not very difficult to do in the next part. So I believe that all of you can try and solve that by yourself. Okay, so we'll finish this class here. If you do not have any questions, so I just finish the class.
Okay, thank you, madam.
Thank you, madam. Thank you.